We're going to talk about rational functions today. So rational functions are where you have a polynomial over a polynomial. So if p of x is a polynomial and q of x is a polynomial, then we divide those two things, and that would be a rational function. Now we've looked at some rational functions, but they were relatively simple rational functions. So we had looked at something like 1 over x plus 2 minus 3, and we graphed this, and this shifted left 2 and down 3. And then we know from that we had a vertical asymptote at x equals -2 and a horizontal asymptote at y equals -3, right? And then our graph looked along the lines of this. Oops. So when we're looking at this, we have a domain problem because of the fact that we're dividing by a polynomial, right? So we'll have some values that don't work because we don't divide by 0. So we want to look and see what makes q 0 in order to tell what the domain is. Okay? So if we look here at these options that we have, what we want to do is we want to solve the denominator to see if there's any value that makes it 0. So this one is linear. We know it's linear because it has a highest power of 1. So if I set x plus 5 equal to 0, then we subtract the 5, so x is -5. So our domain is x cannot be -5. If you use interval notation, it would be -infinity to -5 with a parenthesis because we don't touch -5, and then -5 to infinity. Okay? I'm okay with this notation, but be aware that you should be able to tell what the interval notation is as well. If we look at this one is quadratic. Now to solve a quadratic, we know that you can factor it, or you can use the quadratic formula or completing the square. This one is factorable. It's a difference of squares. So if I set x squared minus 4 equal to 0, we are multiplying to 4 and adding to nothing. So that's 2 and -2. So then we get x equals plus or minus 2. So our domain is that x cannot be those two numbers because that's what gets the denominator 0. Okay? So again, in interval notation, this would be -infinity to -2, -2 to 2, and then 2 to infinity. All right, so the problem, or the thing with rational functions is that your interval notation becomes lengthy because you can have multiple values here. So it becomes lengthy to write. So generally it's accepted to do x cannot equal, and then you list off the things that it cannot equal. Okay. If we look at this one, notice here we've got x squared plus 1. If we set that equal to 0, this is not factorable because I can't multiply to 1 and add to nothing. We could use the square root property. So if I subtract 1, I get x squared equals -1. And then I want to undo the squared. So I'm going to take the square root of both sides. So then this equals plus or minus I. Okay. Well, plus or minus I does not show up on a graph because it's a complex number or an imaginary number. So we don't need to worry about this. So our domain on this one is all real numbers, which we represent with an R, fancy R, or you could do -infinity to infinity. If we look at this one, we have x minus 1 is linear, so I do x minus 1 equals 0, so I'm going to add 1 to the other side. So x is 1, so that means that our domain is x cannot be 1. Now graphically, so some of these lines somehow got messed up, or the graph got shifted. So this graph should really be right here. This graph should really be here. And this graph should be here. Sorry, I don't know how that didn't copy well. So if you look at the blue parts of the graph, we want to look at what the domain is from here. So notice we've got this part where there's no x value here. It's also a vertical asymptote. So we have that our domain is x cannot be, we've got 1, 2, 3, so -3. And then we also have that same scenario over here at +1. So we have where x can't be -3, or +1. In interval notation, it'd be -infinity to -3, -3 to 1, and 1 to infinity. So you can also get the domain from the graph. Same problem on this one. We should have the graphs got slid to the side. Oops. So here, if we look at the green parts of the graph, there's no x value here and there's no x value here. So that means that our domain is x cannot be 1, 2, 3, 4, -4, or 1, 2. And then again, in interval notation, it'd be -infinity to -4, -4 to 2, 2 to infinity. And all of those have parentheses because we're not touching -4, we're not touching 2, but we're getting as close as we can to those values. So that's why we use the parentheses. Okay. Now, we also can find our x and y intercepts. So x-intercepts is when the y value is 0. Right? This is true for all graphs. So anytime we're solving for the x-intercept, you let y equal 0 and you solve for x. Now, for our y-intercept, the x value is 0 for every y-intercept. So we let x equal to 0 and we solve for y. Now, in the case of this, we have fractions that we're looking at, or rational functions that we're looking at. So when I set this equal to 0, if I set 0 equals 2x squared minus 4 over x plus 5, if I think in terms of a fraction, what's the only way that you can get a fraction to be 0? Well, the only way that you can get a fraction to be 0 is if you have 0 over some number, right? So when we're looking at the x-intercept, I don't actually care about the denominator at the moment because of the fact that we are only caring about the top because 0 over any number will give us the x-intercept. Okay? So if we look here, our top is quadratic, so we have 2x squared minus 4. So if I set that equal to 0, we could solve, there's a common factor of 2, so I could factor it out and then see what I could do, or we could use the square root property. If we factor out the 2, we've got x squared minus 2. This is a difference of squares, but this one's not a perfect square. You could factor it so that you just are going x plus root 2 and x minus root 2. You probably haven't seen it like that, but it should make sense to you. If we solve with the square root property, either from here or from here, that's when we get the x squared by itself. So if I move the 4 to the other side, I get 2x squared equals 4. I divide by 2, so x squared equals 2. Well, then I want to get rid of the squared, so I take the square root. When we take the square root, you have to do plus or minus, so you get x's plus or minus root 2. If we do it on this one, we end up with moving the 2 to the other side, and then we're right here, and you get the same thing. So our x-intercepts here are plus or minus root 2. Now, our x-intercepts, just like in our polynomials, have a multiplicity. So each of these have a multiplicity of 1, and they're going to cross at the x axis instead of bounce, because our multiplicity is odd. Okay, so that's similar to how we have our polynomials. Okay, so if we look at this one, oh, I didn't do the y-intercept. So that's our x-intercept. Okay. So we would have plus or minus root 2, 0 are our x-intercepts. And then for our y-intercepts, we're just going to find r of 0. So if I plug in 0, I get 2 times 0 squared minus 4 over 0 plus 5. So 0 squared goes to 0, times by 2 is 0, and then minus 4. So we get a minus 4 on top. And then on the bottom, we do 0 plus 5, so we get a positive 5, so we end up at -4/5. If you remember from polynomials, your y-intercept is always your constant. So if we have a polynomial on top and a polynomial on the bottom, our y-intercept is going to be the ratio of the constants. So notice here this ratio is -4, which is the same thing as here. So our y-intercept is 0, -4/5. Okay. If we look at this one, for our x-intercepts, we want to set the top equal to 0 and solve. So if I set 1 equal to 0, that's never going to be true. So this one has no x-intercepts. So then I'm going to look at, okay, well, what's our y-intercept? Well, the y-intercept we find by doing r of 0. So I'm going to do 1 over 0 squared minus 4, but 0 squared is 0, and then minus 4 is minus 4, so this will be a -1/4. Or if you look at the ratio of the constants, it's negative 1/4. If we look at this one, we have on top for our x-intercept, we set the top equal to 0 and we solve. So if I have x cubed equals 0, well, I don't want x cubed, so to get rid of x cubed, we take the cube root. So then I have x is the cube root of 0, which is just 0. It still has a multiplicity, so its multiplicity is 3, which means that it's odd, so it's going to cross at the x-axis. If we look at our y-intercept, that's going to be r of 0, so I do 0 cubed over 0 squared plus 1. 0 cubed is 0, 0 squared is 0, plus 1 is 1, so 0 over 1 is 0. So notice our x-intercept and y-intercept are both 0, which I should be anticipating. If you get an x-intercept of 0, then you know that your y-intercept also has to be 0. If we look at this one, notice here that we've got on top x squared minus 1. So if I factor x squared minus 1, it's the difference of squares, so it goes to x plus 1, and x minus 1 equals 0. So our x-intercepts are at negative 1 and positive 1. Okay. And then on the bottom, notice here that we have an x minus 1. So if I rewrite this in factored form, so x plus 1, x minus 1 over x minus 1. Okay. So notice here that we have a common factor on top and bottom. So if this is a case, instead of this being an x-intercept, it turns into a whole. Okay. So this reduces, so the x-intercept that we get from this turns into a whole. So this turns into a whole rather than an x-intercept. So a whole is just a lack of a point. Okay, we'll talk more about this later, but that's the general idea. Okay. Now, if we look at these, again, our graphs are a little off, which is a bummer. Yeah, that's good enough. So if we look at our x-intercepts from here, we're at negative 2. And I'm going to call that a half. You're just judging off of a graph, so that is fine for estimating purposes. Notice that they both cross, so they're going to have a multiplicity of 0. Sorry, not a multiplicity of 0, a multiplicity of 1, so or 3 or anything that's odd. Okay. Now our y-intercept here is going to be at 2. Notice this one. Let's just have, we're going to move the lines instead of the asymptotes instead. So notice here that we have this x-intercept, which is also our y-intercept. So our x-intercept is at 0, 0. Our y-intercept is also at 0, 0. We know that this crosses, so we know that the multiplicity on this needs to be odd in order to make it cross. So those are how we find our x and our y-intercepts. So now we have our vertical and horizontal asymptotes. So we're still talking about our rational functions and how we get those vertical and horizontal asymptotes. Okay. So R has a vertical asymptote everywhere Q of x equals 0. So anywhere the bottom equals 0, that's a vertical asymptote. And then we have this part here that says unless the factor from the denominator can be canceled out with a factor from the numerator. So it turns into a whole. Okay, so that was kind of the situation that we looked at up above. So notice here, if I look, there's nothing that's a common factor on top and bottom. So if I look at the bottom, our vertical asymptote would be at x equals 0 and then at x equals 2. So whatever makes those factors 0. Okay. If we look here, notice it has a common factor of x. So we have a vertical asymptote at 2 from this one, but the one that got canceled, we have a whole at x equals 0. Okay. So when we're looking at our vertical asymptotes, you have to pay attention to both the top and the bottom to decide if it's going to be vertical asymptote or if there's going to be a whole. So if I look at this one on the bottom, I'm factoring it. So it gives us x plus 2 times x minus 2. There's nothing to factor on the top, so I have no common factors on top and bottom. So that means, oops, I don't want domain. Our vertical asymptote is x equals plus or minus 2. Now, with our vertical asymptotes, you also have multiplicity. Okay, so here, both of these have a multiplicity of 1, so they are odd asymptotes. Okay, we'll talk more about what happens with an odd asymptote later, but know that you can have the multiplicity and decide if the asymptote is even or odd. Okay, so if we look at this one, we want to, if I factor the denominator, I'm multiplying to 2 but adding to 3, so 2 and 1. On the top, we're multiplying to negative 2 because I do c times a, but adding to 4, which is not factorable, which means I would have to do the quadratic formula, which means if it's not factorable, it's not going to be a rational number. So I know that there's nothing on top that's going to match anything on bottom. So then we know that our vertical asymptotes are at x equals negative 2 and x equals negative 1. Both of them come from an odd power, so they're going to be odd asymptotes. Okay, if we look at this next one, we're going to have, if we want to check and see, this is linear on the bottom, so I would have a vertical asymptote at x equals negative 5 unless it has a common factor with the top. So if we look here, we want to say, okay, well, we're multiplying to 6, but we're adding to negative 5. So I could use 1 and 6 or 2 and 3. In order to get to negative 5, but multiply to positive, I would need negative 2 and negative 3. So then whatever way you're factoring, you can get there. I'm going to put my a value on top of both of these, and then I'm going to reduce these ones, so then that gives me 1 and negative 1, and then 2/3. So then I'm going to have 2x plus 3. Oh, sorry, it's a minus. 2x minus 3 times by x minus 1 over x plus 5. So there's no common factor on top and bottom, so I don't have any hole, so I'm going to just have my vertical asymptote be at x equals negative 5. Okay, so if we look at this next one, I've got, this is a difference of squares, but this one's not a perfect square, so I think, okay, can I multiply to negative 8 and add to nothing? No, so there's not going to be any rational factors on top. If we look at the bottom, I've got 2x squared plus 3, so we can solve with our square root property. So I have 2x squared equals negative 3, so I'm going to divide by 2. So x squared equals negative 3 halves, so I'm going to take the square root plus or minus, so x equals plus or minus I root 3 halves. We could rationalize this, I'm not going to worry about that. So this is imaginary, so that means that we don't have any vertical asymptotes on this because we got imaginary numbers. Okay? If we look at this one, notice here that we've got on top a common factor of x, so then we get x squared minus 2x minus 3. On the bottom, I'm trying to multiply to 5, negative 5, but add to 4. So if I do 5 and 1, I need the 4 to be positive, but the 1 to be negative. So that gives me that value. On top, we still have this part left over. So if I'm trying to multiply to negative 3, but add to negative 2, I've got 3 and 1. But 3 needs to be negative, 1 needs to be positive. So then I add to a negative 2, but multiply to a negative 3. So notice we have nothing on top and bottom that is the same. So our vertical asymptote would be x equals 1 and x equals negative 5. Okay. If we look at this last one, if we want to look at this one, we're trying to multiply to 6, but add to 1. So we would use 2 and 3. I need 3 to be positive, 2 to be negative. If I want to multiply to negative 8 and add to 4, 2 and 4 doesn't work. 1 and 8 don't work. So this one is not factorable, so it's not going to come up with any rational numbers here. So I'd have to use the quadratic formula on that one. So notice we just have our vertical asymptote at x equals 2 and negative 3. And these are also odd because they came from the first power, so both of those are odd asymptotes. I neglected to this one, but both of them are odd asymptotes as well. Okay. So then we have our horizontal asymptotes. So there's 3 scenarios that you could have. Okay. Remember that we're looking at P of Q is on top, or sorry, P of X is on top and Q of X is on the denominator. Okay. Remember the degree is the highest powered exponent. So if P of X, the degree of P of X is less than Q of X, then it has a horizontal asymptote at y equals 0. So if the bottom is bigger, then it's y equals 0. Okay. Case 2 is where their degree, so notice on all of these we're looking at the degree of the polynomials on top and bottom. So the degree then if they match, then R has a horizontal asymptote at the ratio of the leading coefficients. Remember, leading coefficients is the one with the highest degree. Okay. So if we look here, x squared and x squared match, so the degree of P of X and Q of X are the same. So I take this ratio here of the 3 over 2, and then our horizontal asymptote is y equals 3/2. Okay. Then we've got if the degree on top is bigger, then we're going to have what we call an end behavior asymptote. It's sometimes referred to as a slant asymptote, but no horizontal asymptote. Okay, so we'll talk later about how to find the slant asymptote or the end behavior asymptote. Sometimes it's also called oblique asymptote. Oblique. Yeah, that looks weird, but I think that's fine. So those are all talking about the same kind of thing. Okay? So we're looking at the degrees of each of the polynomials. If the bottom is bigger, it's y equals 0. If they match, then it's 3/2. And if the top is bigger, there's no horizontal, but there is an end behavior, a slant, or an oblique. All of those words mean the same thing. Okay? So if we look here, this is a squared and this is a first power. So this would have no horizontal. We are going to find the end behavior. No horizontal, but you would have an end behavior asymptote. Okay. Now, to find the end behavior asymptote, you actually divide. Divide. So here, since we're dividing by a linear amount, I can synthetically divide. So I've got 4 is here, 3, -6, 2, bring down the 3, that gives me 12. This gives me 6, that gives me 24, and then that gives me 26. Now, on our end behavior or slant or oblique asymptote, we don't actually care about the remainder. The remainder is negligible, right? When we're talking about the end behavior, we're talking about as we go to the very, very far ends of the graph, what's happening. So if I have some remainder amount, it's going to be very not impactful towards the far ends of the graph, so to the very far left or to the very far right. So then on this one, it was a squared, so it's going to knock it down to a first power. So our end behavior asymptote is going to be y equals 3x plus 6. Okay. If we look at this one, notice the top is bigger than the bottom, so we're going to divide to find the end behavior asymptote. So there's no horizontal, but there is an end behavior one. So we find the end behavior one by dividing. Now, this is linear, so I can synthetically divide. So we've got 4 here. Remember, we changed signs from here to here. Notice I also skip a power, so it's cubed 1 none. So I need to make sure I put that 0 for the squared. Okay. So I bring down the 1, that gives me 4, that gives me 4, that gives me 16, that gives me 18, that gives me 40 and 32, 72. And then that gives us 73. Yeah. So then this was a cubed, so it knocks it down to a squared. So x squared, x, and then our number. So then our end behavior asymptote is y equals x squared plus 4x plus 18. Okay. So if we look here, we again are comparing our powers. So this has a first power, this has a second power. So the bottom is bigger. When our bottom is bigger, it goes to y equals 0. Okay. The other way that you can remember this, if I were to plug in like 1 million and 1 million, if I square 1 million, it's a much, much bigger number than if I just times 1 million by 2. So I'm going to have a relatively small number over a relatively large number. So a small over a really large number is getting closer and closer to 0, right? So that is why that one works. Okay. If these are matching, like we've got a squared here and a squared here, it's going to be the ratio of the leading coefficients. So we're going to have y equals 2 over 1, which is just 2. Same kind of thing here. If you think, okay, well, if I plug in a million, these aren't going to make a huge difference on the far end. Like a million squared is going to be more impactful than 4 times a million. So what happens is as we get to really, really, really large numbers, it's going to go to this ratio here because our powers are matching. Okay. So if we look at this one, our highest power is a 2, or the power on top rather, the degree on top is 2, and then our degree on bottom is 1. So the top is bigger, so there's no horizontal asymptote, but there is an end behavior asymptote. So I'm going to synthetically divide. So I have 2, -5, 3. So that gives us -10. That gives us -15. That gives us 75. And then again, we're not caring about our remainder for our end behavior asymptote. So we get, it was a squared, so it's going to go to 2x minus 15 because we knock it down by 1 power. Okay. If we look at this one, the squared and the squared, so those powers are matching. So what we're going to do is we're going to take the coefficients of the leading coefficients. So we get 8 over 2, which is 4. If we look at this one, okay, we're going to see that the top is bigger than the bottom. And then this is where we're sad because this is not linear. So that means that I have to long divide these two values. And so x squared plus 4x minus 5 goes into x cubed minus 2x squared minus 3x. So if I do x cubed divided by x squared, that gives me an x. X times x squared is x cubed. X times 4x is 4x squared. X times -5 is -5x. I change the signs. So that gives me -6x squared plus 2x. So I'm going to do 6x squared divided by x squared, which gives us 6. And then I'm going to do, I probably should have used a different color. 6 times x squared. Actually, I don't care about the rest. Notice here that this is our constant. Again, we don't care about the remainder, so I don't care about the rest of it because the rest of it's just going to be my remainder. So notice here we had the matching powers. So if I knock it down, then my next one's going to be a power that's lower, which means that that's our remainder. But we don't care about remainders, so I can just stop there, and then I get y equals x plus 6 for our end behavior asymptote, or slant asymptote, or oblique asymptote. Okay. Then if we look at this one, we've got a power of 2 and a power of 2. So our ratios are the 1 over 1, so then we get y equals 1. So that's how you find your properties for your rational graph.